going to look at the basics of trigonometry now. And pretty much if we wanted to take things from the beginning, then we could think of trigonometry as an attempt to be able to guess the lengths of the sides and the angles of a triangle out of the least possible amount of information. So in general, a triangle has three angles and three sides. But we know from elementary Euclidean geometry that we don't need all 6 elements of the triangle in order to define a triangle. In particular, 2 sides and the angle in between are enough. Or 3 sides are enough. So for example, if you know the 3 sides of a triangle, how do you guess the angles of the triangle? Or one side and the 2 angles adjacent to it are also enough. So in each of these cases, how do you find the remaining elements of a triangle if you know the ones that uniquely define it? So that's one question that we would like to be able to answer in trigonometry. But the interesting thing is that initially, instead of just studying any triangle, we just study right triangles. So in classical trigonometry, we take a right triangle. Let's say we call one of its sides, one of its angles, theta. And once you have fixed this acute angle, the triangle has 2 acute angles and 1 right angle. So we fix 1 acute angle. Then the side that lies across from it is called the opposite right side. The side that is adjacent to it is called the adjacent right side. And of course, you have the hypotenuse. And the main remark here is that if you take 2 triangles, 2 right triangles that have the same acute angle, then the corresponding lengths are proportional. So look at these triangles. They're, as we say, similar triangles. So if we take, for example, how many times the opposite right side fits in the hypotenuse, when I say opposite right side, I mean opposite to theta, then if I compute this ratio for any of the 2 triangles, I will find the same answer. So early trigonometry was pretty much an attempt to tabulate all these radii. So we had to name them first. So the sine of the angle theta was defined as the opposite right side over the hypotenuse. The cosine of theta was defined as the adjacent side, right side over the hypotenuse, the quotient, how many times it's the adjacent side fits into the hypotenuse. And finally, the tangent of theta was the opposite right side divided by the adjacent right side. Interestingly enough, we also have the reciprocals of all these numbers. So the reciprocal of sine, it's called cosecant. It's denoted by CSC. So that's the reciprocal of sine. Then the reciprocal of cosine is called secant. And the reciprocal of tangent is called cotangent. The reason, I mean, if you think about it, we could pretty much work with just one of these 6 numbers. The reason we choose to work with all of them is because some formulas, some relations become especially simple if you use one of these numbers over the other. So that's why we are going to pretty much think of these numbers as the standard trigonometric numbers attached to an angle. This approach has some obvious limitations. So for example, in this case, the angles that we're talking about, if we count them in degrees, are always going to be between 0 and 90 degrees because we're talking about acute angles. Any non-right angle in a right triangle is acute. This really seems as an unnecessary restriction, and we will try to raise this restriction pretty much right away. However, I do want you to understand that people did make measurements of these trigonometric numbers, and the tabulation of all these numbers for at least the integral degrees was one of the early successes of trigonometry that really allowed people to do exactly what I described in the very beginning. You have a triangle, you know 3 elements of that triangle that absolutely define it. You can find the remaining 3 without too much difficulty. In most cases, you will need a small approximation, but usually the measurements that you're going to get are going to be quite precise. So that's in some sense early trigonometry. And it is useful to know some of these numbers. So just to give you an idea. So for 30, 45, and 60 degrees, the sine is correspondingly 1/2, square root of 2/2, and square root of 3/2. And the cosine goes the other way. And we have square root of 3/2, square root of 2/2, and 1/2. Then we have the very important Pythagorean theorem that says that the square of the sine plus the square of the cosine of the same angle is equal to 1. And actually, if you divide through by the cosine, then you get another kind of interesting relation. You get that tangent square of theta plus 1 is equal to secant square of theta. This can also be thought of as another expression for the Pythagorean theorem. Now, how are we going to raise the limitations that we described before? So the first thing that we do is we introduce a new way of measuring angles. If you think about it, the degrees is a rather arbitrary way to measure angles. I mean, why is the full circle 360 degrees? I mean, there's no really good reason for that other than some interesting angles can be measured in with convenient numbers. There's nothing else. There's a much more compelling way of measuring the circle, and that's the following. It all starts with a unit circle. That's a circle of radius 1. And it turns out that the circumference of the circle, the circumference is 2 pi. In fact, pi can be defined as the ratio of the circumference to the diameter of any circle. So now here's what we do. We decide to attach to the full circle the number 2 pi and call the corresponding unit radians. So the full circle, meaning 360 degrees, is 2 pi radians. And then, of course, we will have that 30 degrees will be pi over 6, and 45 degrees will be pi over 4, and 60 degrees will be pi over 3, and 90 degrees will be pi over 2. These are some of the most important angles that we have. But now there is something else which becomes really interesting in the case of the unit circle. If you take any arc that starts at this point, which is considered to be, so this is the point 1, 0, which is the start of all considerations, then the length of the arc numerically is equal to the measure of the angle in radians. And you can see why this is true very easily, because the length, the circumference of the full circle is 2 pi, and also the whole, the full angle, the whole circle, in other words, measures 2 pi in radians. And for that reason, they're pretty much, whether you measure the length of arcs or you measure angles, it's pretty much the same thing. So that gives us a very nice way of extending the trigonometric numbers to pretty much any real number. So here's what you do. Start with the number x, go to the unit circle, and find an arc that has measure x. Okay, please note that this x could be greater than 2 pi, so you would have to go more ways around. It could be even a negative number, in which case you will do your rotations clockwise, meaning the positive direction is the counterclockwise and the negative direction is the clockwise. The bottom line is that you will end up with a point on the unit circle. Once you find that point, then its projection onto the horizontal axis is the cosine of x, and the projection onto the vertical line, onto the vertical axis, is the sine of x. Of course, once you have defined cosine and sine, all the other trigonometric numbers can be defined quite easily. And now you get functions that are defined for all real numbers, and they have very nice graphs that pretty much repeat every 2 pi. So this is the graph of sine. The graph of cosine is exactly the same. It's just shifted by pi over 2. So this is cosine x. The graph of the tangent looks a little stranger. So the tangent, exactly because the tangent of the cosine, which is the denominator of the tangent, at I forgot to say that the tangent can also be defined as sine over cosine, and cosine of pi over 2 is 0, cosine of negative pi over 2 is 0. So you see tangent blows up at the numbers pi over 2 and negative pi over 2. Later we're going to see that this situation is described as having an asymptote. So if we would like now to revise a little the table that I gave you before, now we could use a few more angles. So let's say 0, pi over 6, pi over 4, pi over 3, pi over 2. For sine of 0 is 0, and then we have the numbers that we gave before. So 1/2 square root of 2 over 2, square root of 3 over 2, 1. For the cosine, it's exactly the same numbers going the other way around. So 1, square root of 3 over 2, square root of 2 over 2, 1/2, 0. And for the tangent, this is going to be 0. This is going to be 1 over square root of 3. This is going to be 1. This is square root of 3. And this is undefined. Yeah. And then you can compute if you like for cotangent and secant and cosecant and, all the other trigonometric numbers. There is actually a fun mnemonic for these numbers. You can, for the sine, you can see that this is the same thing as square root of 0 over 2. And this is square root of 1 over 2. And this is square root of 2 over 2. And this is square root of 3 over 2. And this is square root of 4 over 2. So you see how you pretty much have all the consecutive integer numbers here, 0, 1, 2, 3, and 4. Okay, it's actually quite interesting. You can use it if all of a sudden your brain stops and you can't remember what the trigonometric numbers are. This can come pretty handy. I should mention here there are many trigonometric relations that are especially useful. And I could mention the double angle formulas. I'm not sure we're going to use them that much, but sine of 2x is 2 sine x cosine x, and cosine of 2x is cosine square of x minus sine square of x. This can be written also as 1 minus 2 sine square of x, and 1, or rather 2 cosine square of x minus 1. So a lot of interesting things are going on here, and the trigonometric functions, the 6 trigonometric functions, sine, cosine, tangent, cotangent, secant, cosecant, are going to be pretty much our bread and butter while doing calculus. So there are so many things that we're going to want to do with the trigonometric functions. At some point, we're also going to identify some interesting relations between the trigonometric function and the exponential functions, two functions that seemingly are completely unrelated, at least if you look at how we introduce them. So this is pretty much all the very small piece of trigonometry that one needs to know for our course. And hopefully we're going to refresh our memory on all of these facts as we go. One of the things that is going to be totally absent from our treatment of calculus is the inverse trigonometric functions, meaning the way that the inverse of the exponential function is the logarithm, the way that the inverse of the logarithm is the exponential function. One can define inverses for trigonometric functions, but we're not going to follow that perspective at all. That's all we need. Thanks for watching.